Ready?
Yeah, start already.
Okay, so here we go. We got power to the unit. We're gonna go ahead and kick it on. And you can see when we, oh, she's tripping out on overload. We're gonna put it on AC amps and then make sure that we got a good connection in here. And then you can see right here, 33.7 lock rotor amps right there. So that's not the true amperage with the RLA, the running load amps. To get the running load amps, grab me a screwdriver out of that toolbox there. We're going to make a circuit jump from here to here, and that's what this capacitor does. And there's all kinds of relays that are designed to take it out of the circuit. Like this is a current relay where it uses the power that's coming through. It's building up so much magnetic force with the amp draw that it pulls a magnet down with enough force and breaks the circuit to the start winding. And then there's a potential relay where it actually, if you could take a look here at these windings, the bigger winding is the start winding and the smaller winding is the run winding. So when we take the start winding out, it actually has a magnet going through a magnetic field with the wires that's creating a little bit of power. So it's actually a generator. So it could generate more voltage that we're supplying to the circuit. So it might have 120 volts coming in, but coming out it could be 170 volts. And the more voltage will allow the relay on the start winding to energize. So the 170 volts on the coil will trip a circuit out to stop the power from going through the start winding. If the start winding usually gets left energized, some start kits do that, like these here have been known to go bad and then cause the start winding to stay energized in the circuit. That'll burn out the winding. And then these, I've heard rumors from some technicians that they just technically they burn out the windings anyway. They're not the best to use from some technicians I've seen. So I'm going to go ahead and energize the start winding by turning on the power and then creating that spark. And that's what the capacitor's doing. It's got to delay it about a second because it's the same phase, the same sine wave of voltage. And by delaying where the voltage will lag, it will delay it enough to kind of make a different phase for the compressor to trick it to think that it's got another 120 volt circuit to energize the motor. Now look at these capacitors. Pretty much what a capacitor is. A lot of people ask me a lot of questions about capacitor. So here's what's happening in the book. This book here's the latest modern refrigeration book. But here's where we got the current, where the amp field is going before the voltage in the start winding. So this is the run winding here, and then you got the start winding where it's a little bit delayed. What I did there, I held it back for a second, hit it with the screwdriver in between here to here, and that energized the circuit. And then I took the screwdriver away, and that broke the circuit. So it didn't stay energized for long. But here pretty much what you got is if I was to cut one of these open, now be careful because back in the 60s, they used these things called PCBs. Had a very sweet smell. In fact, there was this thing called the Love Canal, which is a Superfund site up near Buffalo, where GE made a bunch of these capacitors with this toxic material called PCBs, polychlorinated butylanes or something like that. And they buried them. And then they buried them with clay over it. And then the clay got broken when some construction company came in and bought the land real cheap to build track housing. And then those people that were in those homes started having kids with defects and things like that. And they figured out it was from the PCBs, from capacitors, from way back in the early 40s and 50s from GE when they used to dump back in an area where nobody was back then. So, you know, nothing against GE, they're a great company, but back, you know, they used to not know. So you got to make sure if you're going to cut one of these open, I don't advise cutting any of them open, but no PCBs, okay, no PCBs. Or if you're ever using them, no PCBs. When we first came into this program, this classroom had a sweet smell to it. And it had back in a cabinet, opened up the cabinet, it had a bunch of capacitors because this program's about 50 years old. And it had a bunch of capacitors from the early 50s. And those capacitors all had PCBs. So for a long time, people were coming into this classroom smelling and breathing that air, including yours truly. As a high school student, it always had the same smell as when I came back and started teaching. And they had to come back and they had to get some guy, one of their safety security guys, give me some stuff. And they made me clean it all up. You know, I guess I'm qualified. But they made me clean it all up. But here we go. So pretty much if you were to cut one of these open, all it is aluminum foil. It's really aluminum. And they take a dielectric material. Now, a dielectric material is like a resistant to electricity material. Like this is wax paper or parchment paper. And all they're doing with the electrons, you know, we talk about electricity and voltage and electron flow, is that they're letting all the electrons build up on one plate. And this is happening in seconds. This is happening in split seconds. So these electrons here are all going to build up on one plate. And when you unroll one of these, we've unrolled a couple of them. And they literally go from here all the way to the other end of the parking lot. They are really long plates. So they get really long and big. And depending on the size, whether it's a 7.5 cap or this one here is a 20 microfarad cap, all right, that's the rating in microfarads, determines how much area this has, okay? And then there's a fancy form on Wikipedia, and this is some physics level stuff right here that talks about how these capacitors work in the surface area. But all we're doing is we're going to build up a bunch of electrons onto this plate. It's almost like if everybody started piling onto a bridge. And then eventually those electrons are going to jump through the dielectric material to the other plate once the bridge gets full. So it's almost like if everybody's piled on the bridge and the people that are standing next to the bridge edge right here overlooking the water and more people come on the bridge, what's going to happen to these people right here? Yeah, they're going to jump off. They're going to be jumped off. They have to be pushed off. And that's what happens here with the electrons. And that time that it takes to go from this plate to this plate is a split second, a millisecond, nanosecond. It's quick, very fast. All right, and then determining the area will determine the size. Now, when they go bad, usually the round ones are start and the oval ones are run caps. The run caps just help the efficiency of the unit. They actually go in the start winding parallel to the run winding, but they stay in the circuit to help the efficiency of the unit. The start caps are just to be for starting only. So there should be some sort of device, like some sort of coil, again back to the potential relay or the current relay that takes it out of the circuit. And when they get bubbled up like this is from Elvis. Elvis is a student that graduated 15 years ago, and now he has his own air conditioning company, Service Works. But this was the first capacitor, I remember he brought it to me about 15 years ago, that he ever changed out. And the telltale sign of a bad cap, if you don't have a meter, is if it's bubbled up. And then you can do some special things with these capacitors. Like if you didn't have the right size, you can tie them in series. When you tie them in series, it actually makes it smaller. You can tie them in parallel. So we're going to tie one in parallel, and we're going to take a couple readings. Let me see that meter, Ronnie. You might have to unclip it. All right. And then we're going to need a marker, Randon, from the thing so I can write. I had a marker there, but it's moved. So we're going to go ahead and we're going to take some microfarad readings of this capacitor here. It says on the side that it is a 25 UF plus or minus 6%. So it has a little, and it is 24 microfarads. So 24 microfarads. Randon, it's just on my desk in my desk drawer spine. There you go. And then this one here is going to be a 12 UF. So we got a 25, and then they look about the same size, but it's about half. Thank you, sir. So we got that there, and this one here is a reading about 12.5. So we're going to connect them in parallel first and then measure them. So parallel means, and sometimes they make a dot to let you know which way to connect up. So we got one that's a 12.5, and it read about 12.5, and then we got one that's a 25. So when you tie them in parallel, it should be the total of the two. So if I needed a 37 or 38 microfarad capacitor and I just had a 12.5 and the other size here, the 25, then once I measure it now, it doesn't matter which one I measure it on, but it should be tied in parallel to be, bang, 36. Now remember, we're plus or minus 5%, so there's about a 2 or 3 microfarad swing plus or minus that we have on that. So that's in parallel. That's easy. So you just pretty much for the capacitors, you can tie them when you tie them in parallel, add them up. That's 0, that's 1, and now we got the 38 microfarad cap. Now, when we tie them in series circuits, it's always the reciprocal, whether ever we're doing the series. So series means I'm now going not parallel, but we're going through one to another. And you would think that because you have them both in line, that it's the same thing. You'd add them up. But there's actually a formula you got to do. And HVAC Excellence has got this great little book that tells you that you're going to do this formula here. So we have, where we're going to find the capacitance total, it is C1 times C2 over C1 plus C2. So we got two capacitors. This one's going to be the 25. This one's our 12.5. I need you guys on your calculator to multiply 12.5 by 25 for me. And then we've already added this up. This is going to be 37.5. So whatever the number they're coming up with, we're going to divide that by 37.5. What is that number you're coming up with on that iPhone of yours?
300. No, wait, that's way too much.
Way too much? It might be. 12.5 times 25. 10 times 25 is 250. Then if I was to add another 2.5, it should be 350 and some change.
312 plus 312.5.
312. Is that what you got?
No.
What did you get?
I got 318.7.
318.7?
Yeah.
Wow. We're doing math here. What do you get? You got your phone with you? Do it again. Double check your math. 12.5 times 25.
Oh, 25. I did. Yeah, 312.
312 is the number. That's good. 312. So take 312 now and divide it by 37.5. 37.5. What's our number? What's our math?
37.
I bet I can tell them what the answer is before.
8.3.
Yeah, 8.3.
Check it out on the capacitor. 8.2. Remember, plus or minus 5%. So in series, believe it or not, it's actually, we lowered it. I took a 25 microfarad capacitor, a 12.5 microfarad capacitor, and by tying them together like that, we made it an 8 microfarad capacitor. So we could switch them around any which way. So if you don't have the right capacitor on the truck, and this is what I always had to look this up. You know, I always forgot this little formula: C1 times C2 plus C2, C1 plus C2, divide them, and that finds the total capacitance. So that explains a little bit about the capacitor. We're winding down from all the videos. We're getting towards the end of the school year. Everybody say hello to Mr. Bogan, the automotive technology instructor, the best in Fairfax County. And thank you very much for watching.